Okay, guys and girls, I'm going to do a very basic video on calculus. The main purpose of this is so as we can calculate instantaneous velocity, and later on we'll be calculating instantaneous acceleration. So the first thing, there's two concepts, main concepts that you need to understand. First of all, you need to understand what a tangent is. Tangent is a line that is at right angles to a curve. So if I take the circle and if I take a line coming out from the center, which is basically the center of curvature, and if I take that line to a point on the axis somewhere, then and go right angles to that line, like I have here, then I can draw a tangent. Okay, a tangent should just touch the circle, it shouldn't cut it. Of course, if it's a curve more like the one on the right here, then it's going to touch it here at this point. We'll call that point C, but strangely it's going to actually cut it over here, but no need to worry about that. It's still a tangent at this point because this would tie back to at right angles to the center of curvature up here somewhere. Okay, that's what a tangent is. Hopefully you should all know that. Second thing is something you should all know. I'm not going to go into any detail. The slope of a line, the slope of a displacement time graph gives us velocity. So if I take the slope of a displacement time graph, that will give us velocity. Okay. So this brings us to the next problem: is what happens when my displacement time graph comes up in a curve. Okay. So how do I find the slope of a curve? And that's what essentially differentiation is all about. So you might look at this section here and you might say to yourself, well, this part here looks pretty straight, so I could find x1, y1 and x2, y2 at these 2 points, and I could work out the slope, and that would be fine. But the problem I would have is what happens here and here. Okay, so above at the curvy points, how do I draw a tangent to my displacement time graph when it's in a curved shape? Okay, so what you could do is you could take 2 points that maybe are on either side of a point. You could, let's say, if I want to look at this point here, point C, I guess we'll call it. No, I can't call it point C. I'll call it point G because it's not on the map. I could look at 2 points on either side of it, A and B, and I could say to myself, well, I could find the slope here by just using the rise over the run, or delta x over delta t, and that might give me some bit of a slope, but there's no guarantee that that's going to be the correct slope. Okay, no guarantee. So I need another way. So here's where we come into your mathematics, and you'll be borrowing a little piece from algebra or pre-calculus, and that is the idea of a limit. So what you do is you take what's known as the limit as t goes to 0 of delta x over delta t. So what does that mean? Graphically, what that means is if this here is delta t, I should really use a different color. If this here is delta t, and if I make t go to 0, then what I'm essentially doing is I'm making the length of that line smaller and smaller and smaller. Okay? And hopefully it will come to a point. Sorry, it does come to a point. There's no hopefully about it. It does. It comes to basically a point, or the idea of a point, that will be on our line, okay, or on our curve. And I can now get the slope of my line by using calculus. Okay, this is the basic idea here. You're taking a limit as t goes to 0 to make the difference, the length of that line, or the distance between those 2 points, as short as possible. Okay, and this is what's known as an infinitesimal difference, or an infinitely small. I have it down here, very, very small, an infinitely small difference. So this brings us straight on to differentiation, and here's what you must understand about differentiation. Differentiation, regardless of what it's about, is a rate of change. It's a rate of change of something. From our point of view, it's going to be a rate of change of x over t. Okay, It's a rate of change of x over t, or displacement over time. Or later on, it might be delta v over delta t. Okay, and that will hopefully give us acceleration. This one will give us velocity, and this one will give us acceleration. So there's two main rules that I want you to know for now, okay? Just for now. We'll come to these other ones later on, but the two that I want you to know about is the constant rule, okay, and the power rule, which is here. So with the power rule, we'll start here. If I have, say for instance, so I want you to take this piece down here. Here's my example. If I have y equals 3x to the power of 4, how do I differentiate that? The notation I use is dy dx, okay, which means the change in y over the change in x. That's all it means, okay? So I have to use my power rule to be able to differentiate this. And if I follow what this says, d dx of x to the n, this is the very, very general form. Look at what's happened, okay? My n was there, and my n now comes down and multiplies in front. So my 4 is here, and my 4 comes down to multiply. So I have 4 times, well, I have to keep the constant here, which is 3, times x to the power of n minus 1. So my n was 4, and I subtract away a 1. Okay, let me tidy that up. I have 4 times 3x to the power of 3, okay, which gives me 12x to the power of 3. Okay? So please make sure you follow that from beginning to end. All that happens is your power comes down, multiplies in front, and you reduce your power by 1. Okay? That's it. For the power rule, that's what you do. Okay? Okay, the second example that I'm going to look at is for the constant rule, okay? Because these are the only two we're going to look at for now, all right? Let's say my sum or my question says y is equal to 4. Find dy dx of y, okay? So basically what you're asking is, how does y change with x? Well, I've just graphed it down here. Here's the graph of y equals 4. And if you notice, it's a straight line that goes all the way across to infinitely parallel to the x-axis. So how does y change with x? Answer is, it doesn't. Okay? So for this, for any constant at all, dy dx will be 0. Okay, so that'll make the maths of it a little easier. Those terms, those constant terms, will just fall out. Okay? Okay, so at this stage, I'd like you to pause the video and try these ones yourselves, please. Okay, I hope you got that. So, y is equal to x squared. What do I do? Well, the 2 comes down and multiplies. So I've got 2x. And then I've got reduce this one by a power of 1, by a factor of 1. And that gives me dy dx equals 2x to the power of 1, or simply just 2x. Okay? For this one, x equals 5t to the 6. Again, the 6 comes down and multiplies. So I've got dy dx equaled 6 times 5t to the power of 6 minus 1, which is 30t to the power of 5. Done. Okay? Last one. I've got x equal to negative 4t. Find dx dt. Sorry, I think in the last one I said dy dx, but I meant dx dt. So we'll be more dealing with dx dt than dy dx. In mathematics, you tend to deal with dy dx. In physics, you tend to deal with dx dt because it's changed position over time. So the power here is a 1, so the 1 comes down and multiplies. And I've got negative 4 t, that was a 1 minus 1, so that's 1 times negative 4 t to the power of 0. Hopefully we all know that anything to the power of 0 is 1, so that is simply negative 4. So what do these examples give us? They give us the slope
of the curve, basically. Think about it like that. The instantaneous slope of the curve at any point at all. Okay, so I have another example, a more compound example here. Try this one yourselves. Pause the video now, give it a go. Okay, I'll run through it. So I've got dx dt, and that's going to be 2 times 4t to the 1 plus 3. This t just goes to 1, and this t disappears and I have a 1 multiplying. Okay, this goes to 0. So my answer is 8t plus 3. So again, what does this give me? This gives me a velocity, an instantaneous velocity at any point. If this is an equation that describes the motion of a particle or an object, then if I want the velocity, say for example at t equals to 3 seconds, 3.0 seconds, then all I do is I take my 3.0 seconds and I substitute it in here for t. So v at t equal to 3.0 is 8 times 3.0 plus 3, which is 24 plus 3, 27, and I'm presuming that this is in meters per second. I would have to be given units on my question for that. Okay, final question. Try it yourselves from start to finish, and I'll run through it very quickly. Okay, here we go. So, differentiating this, so dx dt is equal to, I'm skipping steps here now, 10t, because the 2 comes down and multiplies the 5, minus 3. Job done. There you have it. There's my equation for velocity, instantaneous velocity at any point. Just another tiny little side note. Sometimes we write dx dt, sometimes you'll see it written as x dash t, or x of t, okay? This means the same as this, okay? That's it. I hope that made sense. Please leave any questions you have at the end of your puzzle video. Thank you.